Alright, what's up guys? In this video tonight we're going to work on some integration. In this video we're going to strictly focus on integrals that need a U-substitution to be solved. So in other words, this is a video using the method of U-substitution only. We're going to go through about 6 examples. I have it written up here. And U-substitution is a very important technique that you'll need that just won't go anywhere in calculus, and you'll definitely need it. It's probably the most used method there is. Maybe you could make an argument for other methods, but it's very important to know what to do when you get an integral and how to do a U-substitution. So this is really going to help you out. There's going to be 6 examples. You always can't learn with one example, so I have various. The ones I picked aren't too difficult. I just pulled them out of the review section of the textbook. You go to the textbook, if you have the Pearson edition, kind of like what I have here. If you open it up and you go to the U-Substitution section, and by the way, this video may go a little bit long because I'm going to be going through a couple of examples, but you don't have to stay for the whole thing if you don't want to, or you can watch later. So I have the actual textbook, as you can see here, but I like the early transcendentals version of it online. I don't actually have that book on hand, but I do. They have a PDF for it online. I think I'm a little too far with the U-substitution somewhere in here. But that's another good math book to use, calculus book that is really. Oh, here we are. So as you can see here, in the textbook that I have here, basically all I've done is I've gone to the review section here and I've just pulled problems from these review sections. As you can see, I've kind of circled the ones that I've kind of already done because I have ran a lot of the videos on Instagram. I was streaming them, and a lot of these I've already kind of like done on the other website. So I tried to pick something that was different, but we're just gonna go through a couple of these that I picked from this section, just to get us some practice with U-substitution. And then I'm going to do another video, a separate video on integration by parts, because integration by parts is also another important method. And integration by parts requires a little bit more work and maybe a little bit more difficult in my opinion. So in this video, we're just going to focus on U-substitution. I just pulled some integrals from this page here, and we're going to work some of these integrals. I have about 6 examples. I didn't pick ones that were too difficult, but I want to go over that so that you guys will be ready when you see these. Now also, let me be perfectly clear, the examples that I'm going to do are not always going to be the examples that you're going to see. So I highly encourage you to practice on your own, because no integral is the same, and the ones that I do may not necessarily look like one that you may get in class, but that doesn't mean that it doesn't need a U-substitution or it can't be solved with a substitution. And then I'll do a separate video on integration by parts, and I'll do that right after this one. So in that video we won't have as many problems because integration by parts requires significantly more work than a U-substitution, so only there we'll do like 4 problems. But we're gonna go ahead and get started, and if you guys have any questions about this, let me know. So we got 6 examples. 3 of them are indefinite, the other 3 are definite. I wanted to include some definite ones in there because I wanted to stress how important that is when you're doing a U-substitution. So let's start here. So we got the antiderivative of x squared plus 1. And then we got times x cubed plus 3x to the 4th dx. So as we all know in this video, it's a U-substitution video, so there's no ambiguity about what method to use. We already know what we're going to do. My goal in this video is to show you what is the appropriate U to pick. U-substitution is not like integration by parts in the fact that when you pick the wrong U for for an integral with U-substitution, you'll be able to tell whether or not you picked the incorrect thing or not, because you'll get something ugly. Remember, the U-substitution is supposed to make things easier for you. Really, any method is supposed to make things easier for you, but that's what the U-substitution is supposed to do. So if you end up getting something out far more difficult than what you originally started with, that's probably a good hint that you probably picked the wrong thing. Picking the right U comes down to practice. Sure, I can offer you hints and say, well, look for this, look for that, but you have to practice on your own so that you can know what makes an appropriate selection to make. And you have to understand, when you pick something to be U, what's going to happen? What's going to happen to the integral? What's going to happen to the integrand? Are there going to be things that can cancel? You know, you got to kind of weigh those options. So let's start with this one here. So x squared plus 1, and then we got times x cubed plus 3x to the fourth. So the key, we already know it's going to be a U-substitution, but the key idea here, let's just say we didn't know. The first thing I realized here is that if I was going to integrate x cubed, if I was going to differentiate x cubed plus 3x raised to the fourth power, I would use the chain rule. So if I would use the chain rule to differentiate that, in all likelihood, I would use the U-substitution to integrate it. And as you can see here, we have a 4 at the top. This is a U-substitution all day long. Also, you want to look and see if things are cancel out. So the appropriate thing here to pick to be U would be the x cubed plus 3x. You don't want to pick it to be x cubed plus 3x raised to the fourth. You don't want to try to differentiate something too difficult. Well, I mean, that's not hard to differentiate, but it's just it's unnecessary work. You don't want to try to pick that all, unless you certainly have to. So I'm going to pick U to be x cubed plus 3x. And then what you do is you du, you just find that. Take the derivative of that. And obviously, you get 3x squared plus 3. And then you'll simply end up with 1 over 3x squared plus 3 du is equal to dx. Okay. So now, what I would do, I would come over here. So you got your integral, right? You leave your x squared plus 1 in there. That didn't change. You didn't do anything with that. But you do have to put a u inside here now. So now this becomes u to the fourth. And then you'll multiply that by 1 over 3x squared plus 3. Okay. So it doesn't look like we can do much here, because it doesn't look like there's anything that can cancel out. What you can do, we got an x squared here. Well, we do have an x squared there, but it's attached to the 3. Okay. So what I would do in this particular instance is I would just go ahead and factor out a 3. That way we can cancel out the x squareds. I mean, though, we can just get rid of those by doing a little bit of canceling. Actually, matter of fact, we can get rid of the x squareds plus 1 if we factor out an x squared. Because if we factor out an x squared, notice what happens. We have x squared, and we factor that out. Then that must mean that if we take that out, then that must mean that on the inside, I'm sorry, we're supposed to factor out a 3, not an x squared. Sorry about that. Factor out a 3. And notice on the inside we'll have x squared basically plus 1, because if we factor out a 3, and you can always tell whether or not you factored it correctly by simply or distributing back in. If I distribute this 3 back in, I get the 3x squared plus 3 that I originally had before, which tells me that I factored it correctly. Now you see that I have x squared plus 1 and x squared plus 1 here now that I factored it out. So allow me to rewrite that one more time, since I kind of messed up right there on that spot. So this is going to be x squared plus 1, the u to the fourth, right? And then you're going to have, again, 1 over, and I'm going to factor out the 3, and then we'll have x squared plus 1 in here. And what we can do is cancel those out, right? Hopefully that makes sense. Then what we can do at that point, if you notice, we could just write our integrand, or we can just find the antiderivative of u to the fourth and multiply by 1/3, because a 1/3 would come outside, and that'd be times the antiderivative. The only thing that's left over in there, with the exception of the 1 over 3, is the u to the fourth, and then you just differentiate that with respect to u, and obviously you get u to the fifth over 5. You can multiply by 1/3. So if you do that, you have 1/3, and then just sub x cubed plus 3x back in for u. That's all you really need to do there. And so if you do that, you'll simply have x cubed plus 3x that you sub that back in for u. That essentially goes on top, and then down here at the bottom, and you got to put parentheses for this as well, because it's going to be raised to the 5th power, remember. And then we have a 5 down here. So let's just multiply straight across. And if we do that, you'll simply get x cubed plus 3x squared. I'm sorry, not 3x squared, plus 3x, excuse me, raised to the 5th power. And then you got 3 times 5, which is 15. And that's pretty much it. And you just add a plus c at the end. So hopefully that makes sense. So that one was a little tricky. As I mentioned, what I had to do up here, if you got lost, I factored out a 3. Factoring out a 3 gave me the x squared plus 1 that I was looking for, so that we can end up canceling. Because if you notice, we left it this way. There's nothing we could do. There was nothing that could be canceled. So you had to end up factoring out a 3. And I think that was a pretty good example of one to do that had a little bit of, I guess, intuition involved. So that was that one. So we're going to keep going with this, keep working at it. That's the only way we're going to get better at it. Let's just continue to go on with it. So let's move to the next one. I put that right there. All right. So what about the second one that we have here? So the second one that we have here says evaluate secant squared of 3x dx. Again, this is a U-Substitution video, so we already know what method we're going to be using. Like I said, my goal in this video is to kind of just talk to you about what's the appropriate U to pick. So here, unfortunately, unless you're taking business calculus, the trig isn't going anywhere. These trig expressions and functions are just going to pop up and you're just going to see them. And that's just the way it is, unfortunately. But you can make it work. You can make it work. So this is a really easy one to determine what to pick U to be. I would pick U to be what's in parentheses. I typically like to pick something that's easy to differentiate. If it's in parentheses, if it's raised to a power, a lot of times I like to try to pick that to be U. Now, obviously, can be some differences. No all integral is the same. There may be some cases where you don't pick those things. So I'm not saying that goes for all cases. But in this particular case, I'm just going to pick U to be 3x. And then du is just 3 dx. And then we'll have 1 over 3 du is equal to dx. What happens is the 1/3 gets pulled out front. Then we have times the antiderivative of secant squared. Remember, a u replaces where the 3 was. And then you have du here. Then you just take the antiderivative of secant squared of u, which is just tangent of u, multiply by 1/3 and sub the 3x back in. That's all you got to do. So the final answer for this is just 1 over 3 tangent of 3x, put the 3x back in there, and then add the plus c at the end. And that's the solution. Where's my markers? I don't know where my markers went. Oh, here they are. So that's the answer to that one. That one was really easy. It won't all be that easy, but that one was somewhat easy. And that's that one. All right, so that takes care of that one. So now we're going to move to number 3. Number 3 says evaluate the indefinite integral of e raised to the sine x multiplied by cosine x. Now, if you're looking at this, you're like, oh my goodness, I don't even know where to start. Well, what should make your light bulb in your head go off is the fact that what I talked about in the last video. Remember, when you see derivatives in there, when you see, like, for example, if you see a function and you see its derivative in there, it's a good indication that you will use a U-Substitution. Now, we already know that because it's a U-Substitution video, but anytime you see that, then think U-Substitution. Why is that important? Well, if I decided to pick U to be sine of x, well, I know that the derivative of sine of x is cosine of x. So what would end up happening is the cosines would effectively cancel out once I did the U-Substitution, and I'd just be left with e to the sine. Because like I said, I can easily tell what the answer is because I have a picture in my mind of kind of what is going to happen when you do the U-Substitution. That's kind of how you want to approach things like this. You want to take a good look at it, say, hey, this is going to happen when I pick this to be U. This is going to happen when I pick that to be U. It's a good idea, in my opinion, like I said with the last ones, to try to pick U. So a lot of times, and like I said, this can vary, but for the most part, you may end up picking U to be what's raised to the power. But let me just be perfectly clear, that's not always going to be the case. So you have to practice so that when you get in situations like this, you know you know essentially what to do. So what happens is, at this point, we now have the antiderivative, right? Now remember, the sign of x gets replaced with a u, since you picked that to be u, right? You then multiply by cosine of x, and then you multiply by 1 over cosine of x, and then down here at the bottom, these cancel. Does that make, hopefully that makes sense, and it isn't confusing in any way. And then what would end up happening is that you would go down here, and if those cancel, you'd essentially be left with e to the u times 1, which is e to the u. So then you just integrate e to the u du, which is just e to the u, and all you got to do is sub the sine of x back in for u, and then add a c. So the final answer for this is e to the sine of x plus c. And that's pretty much what it comes down to for that one. So that was an easy one. It does look a little intimidating when you first see it. But again, if you ever see that happening, like I said, we see here, we know the derivative of sine of x is cosine of x, so it's almost a dead giveaway what to pick u to be, because the cosine of x's will be eventually cancel itself out. And like I said, this is going to get easier the more you practice. So those are the indefinite. Now I did want to do definite ones because these are important, and I'll explain the reason why in the examples that we do. Okay. All right, so this one we have is from 0 to 1, and we got x times x squared plus 1 raised to the 10th power. And again, it's no ambiguity. We already know what we're going to be doing. The question is, what's the appropriate thing to pick? Well, again, we got x squared plus 1 raised to the 10th power. It would probably be a good idea to pick x squared plus 1 to be u. Again, this can vary, but this tends to happen very commonly. You generally end up picking what's in parentheses, what's raised to a power, something like that. Doesn't happen all the time, but in some cases this is, or in most cases it's like this. You don't want to pick it to be the entire thing, okay? There are some instances, I'm pretty sure out there, the integration is a very complex procedure where you may have to do stuff like that. I'm not saying that there won't ever be a time where you're solving an integral where you don't have to pick it to be just that and a power. But you don't want to make the integral any more difficult to deal with than what you originally started with. So again, it just kind of comes down to practice, and you got to have some intuition about what's going to happen when you pick that to be u. So just kind of, before you even start, just go in with a decent mindset and say, hey, this is going to happen. This is going to, just have a visual of what's going to go down when you pick a certain thing to be u. And then we obviously would just simply get 1 over 2x du is equal to dx. Now, the reason why I wanted to focus a great deal on the on the definites is because this is what gets students all the time. Let's say I bring those down and I put everything in there that was supposed to be in there, right? Let's say I bring all those down. So I have the x, I got u to the 10th, and then I multiply that by 1 over 2x du. Let's say I do that. What's the matter with that? Well, the problem is that we did a U-Substitution and we changed a variable, but we did not change the limits of integration. So no, don't do that. You have to change the limits when you do a U-Substitution for a definite integral. You must change the limits because you're changing the variable. This has to happen when you do U-Substitutions with definite integrals. Change limits with U-Sub for definite integrals. This is something that a lot of students make a mistake on, including myself when I first started. And this will cause you to get the answer wrong 100%. Just that small little step of not writing the limits correctly will screw the whole thing up for you. So I'll talk about how to get the new limits, but when you're doing U-Substitution for definite integral, when after you've done your substitution, you set up the new integral, just leave the integral or leave the bounds blank for the time being. It does. I mean, if you want to find the limits first, I guess there's nothing wrong with that. You don't have to simplify first. You don't want to, it doesn't matter what order you do it in, but you have to make sure that you do it as opposed to not doing it at all. So me personally, I just like to simplify first and then I go through and find the limits. But you can do it in whatever order you want to do it in. It doesn't make a difference, but you just have to make sure you're doing that. So obviously what we'd be left with is u to the 10th times 1/2. So we can pull 1/2 out front, leave u to the 10th on the inside. We can integrate that, but we can go ahead and change the limits. So the way you change the limits is this. You just look at what you set your u equal to, which was x squared plus 1. And then all you do is you take the 0 and you sub it in for x, and then you take the 1 and you sub it in for x, and see what that gives you out, and those are the new limits. So that's what we're going to do in this case. So we'll take the 0, so we'll have 0 squared plus 1. Well, 0 squared is 0, and we add 1 to that, we'll just obviously get 1, right? And then if we go here and we put the 1 in there, so we have 1 squared plus 1. Well, 1 squared plus 1 is just 2, right? Because you get 1 squared is 1, and then, you add 1 and 1 and you get 2. So now the new limits are going to be, I'm actually going to write it down here because we didn't get a chance to. So it's going to be from 1 to 2. And notice that there's a 1/2 that can always be pulled out front. And then you got u to the 10th du. You also want to maximize the opportunity to pull out constants, because a lot of times you'll see things in the integrand and it'll be constants and it'll cause the integral to look more difficult than it is. So remove constants, pull them out front. Don't forget about them. Some people do that. They pull them out and they just throw them away. They don't go anywhere, but you're just removing them for the time being. So get them out of there, because like I said, a lot of times it can make the integral look a lot more difficult than it actually is. And we really already know what this is going to be, other than we just subbing the limits. This is going to be u to the 11th over 11. We know we can multiply that by 1 over 2, and then we just evaluate from 1 to 2, with the 2 going first according to the fundamental theorem of calculus. So the 1/2 just goes out here. Then you can do this bracket if you want to. Then this is u to the 11th all over 11, right? Because of the power rule. Remember, for the power rule for integration, it's u raised to the, not u raised to the, anytime you have a power, instead of adding 1 to the, subtracting 1 to the exponent, you add 1 to the exponent. And so it would be u raised to the 10 plus 1 all over 10 plus 1, which is 11, obviously. And then you just evaluate it from 1 to 2. Also, another common mistake, you have to remember what the fundamental theorem of calculus says, at least the second part, that is, the upper limit is always substituted in first. If you sub in the lower one first, you're going to get it wrong. So keep that in mind as well. That's something that happens typically with first semester calc students. And it's okay if it happens to you. It happened to me too. It's not a big deal, guys. You don't have to be embarrassed by making mistakes with integration, because this is a very difficult process to learn, and it comes with practice. And unlike derivatives, we don't have really any rules. Like for derivatives, we got chain rule, product rule, quotient rule. We got all these different rules. Whereas with integration, we don't really have rules. We got techniques, like U-Substitution, by parts, all that stuff. Those aren't rules, ladies and gentlemen. Those are techniques to go about solving an integral. And either one could be needed at either time. And also, you want to have a calculator as well, so that sometimes if the numbers end up getting too big, you want to be able to have a calculator so that you can use it. I hate having to give this speech, but I'm going to give it anyway. I'm going to take a brief moment to say it. Please bring a calculator to your classroom. I've seen so many people that bring their phone to class, and they end up in a terrible situation, because if you end up getting an integral that looks something like this, what are the chances that 2 to the 11th power off the top of your head? Not very good. Could you do that by hand? I'm sure you could probably find a way to do 2 to the 11th power by hand, but why would you want to do that by hand? You see what I'm saying? And if you come in with a phone and they're not going to let you use it, then you're without a calculator. And also, if you don't have a calculator, it may impact your ability to reduce things, especially if they're big numbers. You may not know a whole bunch of factors for the big numbers to reduce if you don't actually have a calculator. So please bring a calculator. Also, have a calculator that has a bit of functions on it. This can help you, especially if you're taking something like college algebra, where let's just say you forget what the shape of the graph of x squared is. Well, all you would have to do is just plug it into here. And then if you plugged it into here, it would basically graph it for you. I'm just going to the example, and then you just hit enter. Oops, I'm sorry, not enter. You hit graph. And we all know that the graph of x squared is just a parabola. It just opens up, right? And if it's a negative in front, it opens downward. But my point is that if you have a $1 calculator from the Dollar Tree, which is fine in certain courses, you don't need advanced calculators. But typically, when you're taking the college algebra and the calculus, all that kind of stuff, you want to have something like this. You don't have to have necessarily a graphing calculator. I've had this personally since 7th grade. And that was what, 13, 14 years ago. So I've still works. Graphing calculators are still very expensive. Last time I checked, still $100 if you really want a good one. But they do have some really, really good scientific calculators out there that you can get from various stores that aren't, I've seen some go around $39 if you really want a good one. Some cheaper than that probably. And so that's just my rant on that. For me, I just think that sometimes as students, we have to stop ourselves from causing ourselves to lose points, because the calculus is going to be hard enough on its own for you to try to get through the problems. You don't want to be losing points because you get the arithmetic wrong because you didn't bring your calculator, you brought your phone and your professor won't let you use it. That's something that just happens, and it's going to happen. I promise you, you'll see it. So let's get started here. Let's plug in the 2. And like I said, chances are knowing 2 to the 11 power top of your head are not very good. I have a physics degree and I don't even know what that is. So that's 2048. So that's 2048. And you'll definitely want to have this, because if you don't, you can't reduce. Given the fact that 11 is a prime number, I don't see any way that can be reduced meaningfully. And then we stick in the 1, so you get 1 to the 11th, which is, so you just have basically 1 over 11, basically. And then you just subtract, and so this obviously would give you 2047, and then this would end up giving you basically 11. And then we just take the 1/2 that we have here and we multiply it. So 1/2 times 2047 all over 11. And you just go through and you finish up. So we obviously know we'll just get 2047 on top. 2 times 11 is 22. Okay. I don't know of any meaningful way to reduce that, because the number is just too big. And I don't think it can be reduced either, because 22 is also a prime number. Oh, no, I'm sorry. No, 22 is not a prime number, because 11 times 2 is 22. But I don't know any meaningful way you can actually reduce that. So I don't know of any meaningful way to reduce that. Yeah. So when the numbers get that big, I typically just leave it alone. And for the most part, professors will be pretty cool with it. If it's a number that's super big like that, they might not hold it against you if you can't seem to factor it down any. I don't really see where they would do that. And what you can always do is you can take your calculator and you can just plug the entire thing in there. And the goal is to get out a whole number. If you end up getting out a decimal, then, that's not what you want. Typically, in all the math classes that you're going to be taking, with the exception of statistics, you're going to be using fractions all the time. You're not going to be using decimals really until you get the stats. That's really when you start using decimals. You want to be using fractions. And so if you divide this out and doesn't give you a whole number and the number's too big, you can't think of what's going on, just leave it the way it is. And you maybe have to take a little bit of a risk. I've had to do that before, but if the numbers get too big, I'm just not going to mess with it. So overall, regardless of whether or not you can reduce this or not, that is how you go about the process. So just trying to give a little bit of words of advice at the same time while I'm doing this, because I think it's important. Okay, so you got 2 more. Guys, I'm trying to hold the camera here. All right, so what about this one here? We got 2 more. So you have the integral, definite integral from pi over 16 to the power of 8. We got 8 cosecant square of 4x dx. As we all know, no ambiguity about what's being done. It's going to be a U-substitution. This is another one of the easy ones. This one won't always be easy, but it's obviously the best idea to pick U to be 4x. And then you just go through and you get 4 dx. And then you get basically 1 over 4x du. I'm sorry, not 1 over 4x, excuse me. 1 over 4 du is equal to dx. And so what you do is you take this 1/4 and you move it out front. I'm going to take the 8 and move it out front too, since the 8 is a constant. And so I'm going to just move that out there. I'm going to move the 1/4 out there as well. Now remember, you must leave the bounds blank. We're doing a U-substitution, so you can't just bring down that pi over 16 and pi over 8. That's not a good idea, obviously. And then you'll have cosecant squared, and remember, U just replaces the 4x, and then of course du, right? And that's basically the way it goes. So now we can, change the limits. You can do it whatever order you want to. You don't have to simplify first or anything. You can, if you want to change them early and get it out of the way, then you can do that. Also, the more practice you get with this, you won't even have to write down actually changing. You can actually change them in your head in some cases. In some cases you can't, but in some cases you can easily just calculate what the new limits will be in your head without having to write anything down. So remember that U is equal to 4x. So all we've got to do is sub in pi over 16. That'll give us a new one. That'll give us our lower limit. If we sub in pi over 8, that'll give us our upper limit. So we just sub that in. So that'll be 4 times pi over 16. Well, that just reduces to pi over 4, right? Then we do the same thing for pi over 8. So we just take, we got pi over 8, and then that just reduces to pi over 2, right? All right, so you just plug those in there now. So this will be, this one here will be the lower, which is the pi over 4. And then up here we got pi over 2. And then, your integrand didn't change, just squared. Oh, I'm sorry, we did have the 8 and the 1/4 on the outside, so I don't want to forget about those. And then on the inside here we got U, and then we got du. And so then you just go through, you integrate cosecant squared of U du, and then if you want to, you can multiply the constants out first if you want to. Also, as I mentioned, what order you go about doing things with these integrals is entirely up to you, in terms of if you want to multiply the constants first, if you want to integrate first, and whatever you want to get out of the way, as long as you're not superseding a specific step, like you have to do something in a particular order. But when you're doing this, if you want to change the limits first, you can do that. You're not going to get the wrong answer by doing either one of those operations first, or whatever. And if you want to do that, then that's on you. At the end of the day, I think when we do math or how we evaluate integrals, everybody has their own way of going about doing it. And me personally, if I was a teacher, I wouldn't have a problem with either way, what order you did it in or what way you wrote it. As long as you understand how to get the solution, I don't think people should criticize people's method of actually solving something or what order they choose to do it. So the antiderivative, as you hopefully you remember, of cosecant squared of U. Remember, that's negative cotangent of U. So all we do is multiply these two outside numbers. So we would simply have 8 times 1 over 4, which really just reduces to 2. So we can stick the 2 on the outside. And then remember, antiderivative, that's negative cotangent of U. And then you evaluate that from pi over 4, pi over 2. Okay. Now, luckily for me, I know what cotangent of U, I know what cotangent of pi over 2 is 0. And even if there's no such thing as negative 0, so you can just write 0. And I've also been lucky enough to know that cotangent of pi over 4 is simply negative 1. Oh, is is going to be a positive 1, but we're going to have a negative on the outside. So this would be minus 1, and then you just, that's basically 0 plus 1, which is just, 1. And then you just take the 2, right? And you multiply. So you have 2 times 1, which is obviously 2. That's pretty much the gist of it. All right. Whew. Okay, let's keep going. We got one more to do, and then we'll move to another video. Well, we'll do integration by parts. That's going to be a separate video. So I'm trying to move things around a little bit here. All right, so on our last one here. So evaluate this integral from 1 to 2. We had x times the square root of x minus 1 dx. We obviously know, no ambiguity. We already know what it's going to be. The question here is just picking what's the appropriate thing to pick. This one's pretty easy too. You just pick u to be x minus 1. Or at least that's what I would pick it to be. And then you differentiate that, right? You just get 1 dx. And you basically just get du is equal to dx, to be honest. And then you go over here and remember to leave the bounds blank. You have to leave that blank. And notice that we would end up having, we need to get everything in terms of u's to be doing the U-Substitution. So what I can do over on the side over here is actually solve for x. So we'll have x minus 1 is equal to u. If I add 1 to both sides, that'll make things a little easier for us. So this would be x minus 1 plus 1 is equal to u plus 1. Which gets, obviously over here, that just gives me x. Negative 1 plus 1 is 0. And then over here, I'll have x is equal to u plus 1. So now, because we need everything in terms of u. So this would essentially be u plus 1 multiplied by the square root of u du. Okay. Now, if you want to, yeah, I am going to do that. What I'm going to do is I'm going to go ahead and rewrite this. I'm going to rewrite this as, well, first of all, let's find the new limits first before we do anything. Let me do that part, get that out of the way. So remember, u is equal to x minus 1, so we just sub it. So it'll be basically, it'll be basically 1 minus 1. Okay, that's 0. And then we got 2 minus 1, so that'd be, yes, that'd be 2. So it'd be, yeah, 1 minus 1 is 0. Then we'll have 2 minus, so that's 1. Yeah, so, okay, so what we'll have is, for the new limits, this would be from 0 to 1. Okay, we took care of that. What I'm going to do is I'm going to rewrite this here to make things a little bit easier so we can actually break it up. So I'm going to rewrite breaking it up. So I'll write this as the integral from 0 to 1. And I'll write this as as u raised to the 3 over 2. You can tackle the du on. And then over on the other side, you can do the same thing. I don't want it to look like a separable equation or anything, but I just kind of put them side by side just so you kind of see the behind it. So that'd be a square root of u du. And this will make things a little bit easier for you. So break it up that way if you like. That's just the way I want to go about it. I mean, if you know how to get the answer, whatever way works best for you, then by all means take that. You don't have to do my way. So if I just did power rule here, well, I know that I add 1 to the exponent. 3 halves plus 1 half, 3 half plus 1 is 5 over 2. So I know I'll get u to the 5 over 2 over 5 over 2, which I could just write as 2 over 5, u raised to the 5 over 2. And then you can evaluate that from 0 to 1. If we do that, we'll just get 2/5 minus 0, which is obviously just 2/5. And then over here, we can take care of the next one from 0 to 1 of the square root of u du. Now remember, the antiderivative of the square root of u is just simply 2 over 3 u raised to the 3 over 2. So all you got to do is evaluate that from 0 to 1, and obviously you just get 2/3 minus 0 is equal to 2/3. So now you just take the 2/5 and the 2/3 and you add them. So that's 2 over 5, I'm sorry, plus 2 over 3. This is also another situation where having a calculator, a lot of times you may be given a set of fractions that don't have common denominators. Remember, to add and subtract fractions, you need common denominators. And maybe you know how to do it in your head, and maybe you do, but let's just say, for example, if you didn't know how to do it, you would have to find the LCM of the bottom numbers and then find a common denominator so you actually add them. If you have a calculator, then this isn't a problem for you. The calc will do it for you. But if you don't have one, that's another thing that could probably cost you some points. So what we'll have here is 16 over, what does it say? 16 over 15. And 16 over 15 would be the solution. And that's how you go about it. Alright, so that was 6 examples of U-Substitution. I hope this was helpful. I just wanted to highlight the importance of this method because you're going to use this a lot. It's not going to go anywhere, unfortunately. So you definitely want to practice on your own. Anything in math, no matter what it is, kind of comes down to practicing and working it out from that standpoint. But other than that, that's how you do U-Substitution. I hope those examples were helpful. I'll try to post another video like this in the coming future. So yeah, so that's going to be it. So if you want to join me live for the next one, you feel free to do so. If you don't, you can, look on my look on my Facebook page for the video. But I'm going to move the integration by parts in the next video because integration by parts is a little bit more involved and a little bit more complicated, and I'll explain the reasonings in the next video. I'll see y'all next time.